Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. I give my typical lame introduction. So today we're welcome to have Jin Lee here from the University of Illinois. He's a student of Dan Roth's, finishing up his thesis, and he's going to talk about some of his thesis work. He's got text understanding and mining, which relates a lot to some of the things that we're interested in doing. Go ahead.
So thanks for the introduction. And also thanks for coming to this talk. And so today I will talk about the work I've been doing in the last several years about in my PhD study. And my work focuses on text understanding and mining. And we try to implement concept-based text understanding and mining. So first, let's look at some statistics. So there is a huge amount of text information in the real world. For example, we have more than 8 billion web pages for now, and we have more than 800 million Usenet messages. And every year, the United States publish more than 150,000 new books. And there are also a lot of research papers and news articles. Basically, all of them are text information. Then one big challenge for research is, so when a user wants to find some information about some relevant topic, so how could we build a computer system that can help people accurately find and understand relevant information? So if you have questions or comments, you can interrupt me at any time. So one possible solution is to search information. In an information retrieval engine, given the user can input some keywords. For example, George Bush's foreign policy. And the information retrieval engine will search a large collection of web pages or text, and output the documents that are relevant to the query. And this process is the process of identifying relevant information is done by string matching. So basically, we try to find documents that contain the same keywords as in the query. And there are also many other text-related tasks, like besides search engine, like information retrieval and text mining and question answering. They try to address very similar problem, how to help user find information. And so most current text-related tasks, they identify relevant information based on strings. And we call this string-based text understanding and mining. So typically, we have a large collection of text, and we have a query. And depending on different tasks, we can, like information retrieval, information extraction, the query could be some keywords, could be some database queries, and could be some English questions, like in the question answering system. So then the process of identifying relevant information is done by string matching. So in this example, suppose we want to find some information about Bush's foreign policy. We first try to identify the name Bush in the query. Then we try to search the text collection, try to find the information contain the name Bush or the string Bush. Okay, so we call this kind of task string-based text understanding and mining task. But there is some problem with this kind of approach. One big problem is concept ambiguity in text. Let's see. So previously, so if we return information contain this string, we will return a lot of noisy information that contain that are related to other bushes instead of this bush we are looking for. So okay, so there is a concept ambiguity problem in text. So when we refer to the real world concepts in text, we refer to them using names, like personal names, like locations, like organizations. And there are two problems with string-based processing and these names. So first of all, the name of the same person can be written in very different ways in different contexts. So like the name of Kennedy can be written as John F. Kennedy, can be written as Senator John F. Kennedy, and can be written as Kennedy. Okay. Second of all, the names of different persons can be written in very similar ways in text. So for this person, his name can also be written as Kennedy. Okay. So if we try to find the information based on strings, we would suffer from this kind of ambiguity in text. So our goal is try to solve this problem, and we try to disambiguate names in text. Okay. And the ultimate goal is to implement concept-based text understanding and mining. So previously we searched information by strings. So here the goal is to, so for query, we try to identify which person is mentioned by the query. Then we search the text collection and try to find the information only related to this person instead of the strings. Okay. And the basic idea of concept-based understanding and mining is to understand, to discover, and to access textual information based on real-world concepts. By real-world concepts, I mean people, locations, organizations, companies, or products, all kinds of things. Okay. And there are many related tasks in this direction. So first, the name entity recognition. We first need to extract the names of different concepts from text, and also entity disambiguation and identification. So this is our key task here. We try to solve this problem. We want to know what entities are mentioned by which names, and try to tell. So given me two names, I want to tell whether they refer to the same entity or not, the same person or not. And also, after that, we can do some indexing based on the real-world concepts instead of strings. And we can also integrate information based on these entities. And then there are many applications for this work, like information retrieval, information extraction, question answering. They can all use this kind of this work. Okay, and another major application is semantic integration between text and the databases. So we have a large collection of text information, and sometimes we also have databases. And so the idea is to link them together so we can access textual information very efficiently using database queries. And our focus, so in my thesis work, I focus on this problem. So basically, given some names, I try to know whether they refer to the same entity or not. Okay. So here I will use this simple example to show the key difference between concept-based text processing and the string-based text processing. So given this very simple English sentence, most current text-related text-related techniques, they can understand this sentence, and they will know this sentence means Mary give John an apple. So however, for human being, he knows more. So when he hear about this sentence, he knows this Mary give this John this apple. So there is a mapping from the text segments to the real-world concepts in the mind of a human being. But this mapping is typically missing for a computer system. So most string-based text processing, they can only work on the text segments. But we hope that the text-related task can move from string processing to process real-world concepts. So suppose we understand this sentence, and then we read another sentence, John ate the apple. Then we know it's the same apple, and we link the information together. We integrate different information together. Okay. So this is a very critical direction. And it can influence a lot of task-related tasks. So people have started to look at this problem. So in the entity identification problem in general, there are some people try to find a good similarity metric to match names. And also some people try to, like Bilanco and Mooney, they try to learn a domain-specific similarity between names. So they can tell whether two names refer to the same entity or not. And in the database domain, there is a famous problem called record linkage. And the basic idea is to know, to identify duplicate database records and try to link them together. And in the natural language processing, there is a problem called co-reference resolution. And there are a lot of works in this area. And the basic idea is to cluster noun phrases according to the entities they refer to. But typically, this is done inside one single document. So people try to cluster noun phrases in the same document instead of in different documents. And there are also currently some web-related works in this area. And some people try to disambiguate web appearance of people. So basically try to cluster personal home pages. Okay. In the rest of this talk, I will first give an interview of the problems we try to solve in this direction and also our solutions. Then I will go to some details of the solutions. At last, I will talk about my future research plan. So a basic problem in this direction, how to match names, how to identify entities behind names, is, so given adding two names, whether they refer to the same entity or not. And this is, so one observation is similar names tend to refer to the same entity. Like John F. Kennedy and President Kennedy. They are very similar to each other. So they tend to refer to the same entity. Then the problem is how to measure the similarity between two names. And our solution is we try to use machine learning techniques to learning a similarity metric between adding two names. And we learn this through a pairwise classification task. So basically, we try to learn a classifier that can classify a pair of names into a matching pair or non-matching pair, according to whether they refer to the same person, location, or not. But there are more challenges in this work than that. So we know similar names tend to refer to refer to the same entity. But how about different names? So here, the Michael and Jordan could be names, could both be used in different contexts as the name of Michael Jordan. And, but they look very different. This is the first name, this is the last name. But our observation is, so although they are not similar to each other, but they are both similar to this full name. So there is some connection between names. And then how to, the challenge is how to employ the transitivity between names. And the typical way, intuitive way is to use clustering approach. And we develop a clustering approach that can incorporate, that is different from the existing clustering approach. So we can incorporate label data and metric learning in a unified framework in this work. And this is a brief example, a brief graph of the clustering approach we have, and we call it supervised discriminative clustering. And it's very general. It can be used, applied to other problems. And another challenge is, actually there are more issues we need to consider when we identify entities behind names. So suppose, in this example, suppose we have two.
Are you going to go into details of that question?
Yeah.
Okay,
yeah.
make sure.
Yeah, this is the overview now.
Cool.
Okay, so so here I have two documents, and I know two entities. One is Michael Jordan, the basketball player, and another is Michael Jordan is a faculty in UC Berkeley. And I have two documents that contain the name Michael Jordan and Jordan. But how can we tell which one is referred by which document? So in this case, I need to consider the relation between different entities. Here in document 1, in addition to Michael Jordan, I also know there is an NBA in this document. So then I can probably tell that this document mentions the basketball Michael Jordan. And in the second document, I see Berkeley, so I know it refers to the second person. So I need to consider the relations between entities. And I need to make some global decision instead of just classify a pair of names. Another point here is that the document structure is also important. So here, I know the Michael Jordan and this Jordan, they occur in the same document. So probably they should refer to the same person. And this Michael Jordan and the Jordan, they should refer to the same person too. So I won't link this Michael Jordan and this Jordan to different persons. Okay. So to exploit the information and try to make global decision, we designed a generative probabilistic model to do that. And here is a sketch of the generative model. I will talk about it in detail. Okay, so now that's the overview. Now I will talk about the problems in detail and our solutions. Okay, so first problem is how to measure the similarity between names. The goal is try to find a good distance metric or similarity metric that can measure the similarity or distance between adding two names of people, locations, and organizations. Okay. So we do it. So we try to learn a good distance metric from a pairwise classification task. So the first step is try to learn a good classifier that can tell us whether two names refer to the same entity or not. Okay, and we do this by first map a pair of names into a feature representation. Then we learn a pairwise classifier using the Snow linear architecture developed in our group. Then the activation of the classifier is converted into a similarity metric. Okay, so people have already done that work. So the key difference between our work and the other people's work is we try to get more informative features between names. So for these two names, we try to extract a set of features to capture the similarity between them. And we designed some relational features. The relational features will not depend on the specific tokens of two names, but depend on some relation between the adding two tokens. Okay, so here John and John, we know they are same string, the same token, this kind of stuff, and also nickname, and also editor distance. But by using relational features, by only using relational features, we can suffer from some exception. So for these two examples, the first pair, they refer to the same entity, but the second pair, they do not match. They refer to different entities. However, by extracting only relational features, we will get the same set of features for them. I cannot distinguish them. So we develop a new feature, structure feature, to record the location of the participating tokens in the active features. By using the structure feature, we can tell the difference between those two examples.
Quick question. You really could edit distance or edit the ratio? I think
it's ratio.
Okay.
Yeah, you threshold it. Let me see. It's the real edit distance, but we threshold it. Yeah.
But don't you have to take length into account? Like Kennedy versus Kennedy spelled wrong with one N is one way, whereas John A. Kennedy versus John R. Kennedy, those are both one edited way. The A versus R.
Yeah, but here we only consider editor distance between tokens.
Oh, so
the token-wise features.
Okay.
So I compare John and John here. The editor distance is 0.
Where John in the middle initial A Kennedy and John R. Kennedy.
A
and R are tokens.
Yeah.
Okay.
Yeah, each of them will be token. So we distinguish the case you said by using structural features.
So are you saying?
Go ahead.
Are you saying that the data distance between tokens is the same as the data distance between single characters?
Let me see.
I didn't understand your response to it. So if you take the example John A. Kennedy and John.
So we compute the edited distance between adding two tokens. We don't have the edited distance for two names. We have the edited distance for each pair of tokens. So we compare. So sometimes we can have typos in writing names. So we use that to capture this.
My question was if you have an article about Dylan Hillary.
Okay.
So how to identify uses that go to Hillary and Mr.
Oh, I see. Actually, we have some. Okay.
Because it seems, I mean, you were talking at the very beginning that we're moving the paradigm of matching strings to matching entities and concepts. And
Right.
now, actually, you're looking at the same problem of matching strings. And it seems that you're doing entities and things like that. It's not how you move into the state of concepts.
Oh, I see. Actually, our goal is to know whether two names refer to the same concept or not. But we need to do it using string-based features, right? That's our goal. We identify the concepts from names, then we can do a lot of things. But the process of identifying the concept behind the names, I need to do this kind of stuff to capture the similarity between two strings. That's important information. Okay. So then I go to the second problem. So for different names, I try to find the connection between them. Like Michael and Jordan, they are different, but I know they are both similar to another name, so I want to match them together. So a typical way is to do clustering. To split, so given me a set of names, I just split them all together at the same time into different groups. And there are a lot of work in this area, so people use, so in clustering, we need a distance metric to measure the distance or similarity between adding two names. Then we run a clustering algorithm based on the similarity between each pair of data points. So different distance metrics and different clustering algorithms have been applied to this task. But there are some problems with the existing clustering approach. Okay. So in the traditional clustering approach, the scenario is typically like this. So given a set of unlabeled data points, like a set of names, we try to find a good distance metric and try to find a good clustering algorithm that can partition this data set. So one example is k-means. So we use a Euclidean distance metric, and we run the k-means algorithm to cluster a set of data points. And there are problems with this kind of approach. So if we view the combination of a distance metric and a clustering algorithm as a partition function, as a partition function, then what we do is we have an input data set, and we use this function to partition it, and we get some result. Then there is no learning. There is no learning in this process. We just apply a function, and we get the result. And also, this framework is unsupervised. We don't use any labeled data to help us. Okay. And to solve these problems, some other people also did some work to incorporate metric learning to learn a distance metric for a specific problem, and to exploit labeled data to help clustering. But there are also some problems with these approaches. Okay, so here I just want to give some motivation. Why do we need supervision in clustering? So here I have many data points. And what I want to do is I want to cluster them into 4 groups. So typically, I can find a distance metric to measure the distance between any 2 data points. So these could be the names in the entity identification task. So this is a general approach. So it can be applied to entity identification task later. So here I just talk about it in a general way. So without adding label data, we can cluster these data points in different ways. So we can cluster them horizontally into 4 groups, or we can cluster them vertically into 4 groups. And without label data, we don't know which way is correct, even if we have the best distance metric.
You don't even understand.
I know.
In the concrete case of entities, how do you know how many entities you have? Or Jordan?
That's right. In the entity identification problem, we don't know the K, but here we just assume we know the K. And also in the experiments of entity identification, in this approach, we also assume we know the K. So that's, yeah.
So are you going to talk on how you decide on the K, or you just presume?
Yeah, we just presume. Just like K-means. K-means we assume there is a K. We can try different Ks.
You could do hierarchical.
Right. So there is no difference between this and the K-means. So, but these label data, so if we have some label data represented by different colors, then probably we will know in this case, the correct clustering should be like this instead of vertical. So this example shows the importance of supervision in clustering. Okay. And if we have supervision, we should use it to help clustering. And another motivation for our work is I'll use this example to show that we should learn a distance metric for clustering algorithm and for a specific problem. Okay. So in this example, in A and B, we try to cluster the 12 data points into 2 groups. And in A and B, we use the same distance metric. We use the Euclidean distance metric, but we use different clustering algorithm. We use the single link in A and the K-means in B. Then we will get a very different results, clustering results. Okay. So another point is, in B and C, we use the same clustering algorithm, but we use different distance metrics. We will also get different results. Okay. The point here is, there is no universally good distance metric that is good for any clustering algorithm and for any problems. We need to learn a distance metric for a problem, and we need to learn a distance metric for a specific clustering algorithm. So we cannot learn a distance metric that is good for any clustering algorithm. Actually, a lot of existing work try to do that, and we claim that it's not a good way to do that. Okay. So we propose a new framework for clustering, which we call Supervised Discriminative Clustering Framework. And in the application stage, this is the same as the traditional clustering. We have a data set, we have a distance metric, and we have a clustering algorithm, and we partition the data set. But we add a learning stage to this framework. So in the learning stage, we can use some label data set if we have. Then we have a learner that can help us to learn a good distance metric for a clustering algorithm. Okay. And the goal is to minimize some clustering error here. This clustering error is a supervised clustering error because we compare the clustering result of the hypothesis distance metric with the true clustering of this data set. So this is supervised. Okay, and there are two properties with this framework. The first property is the clustering algorithm, the goal in training, the clustering error is defined in a supervised way. So we can use supervised label data to help us to find a good distance metric that can minimize the clustering error. The second property is we learn this distance metric with respect to a given clustering algorithm. So the clustering algorithm will participate in the learning stage. So the hope is in the application, we can apply the same distance metric with the same clustering algorithm to partition the new data. And the hope is we can also minimize the clustering error for the new data. Okay, so other people also try to use metric learning, but the training stage and the application stage are typically disjoint. So they do not put the clustering algorithm into the learning stage. Okay, so the goal of training is to train a good distance metric for clustering algorithm and to minimize some clustering error. And now the problem is how to define this clustering error in a supervised way. And so we define it by comparing the clustering error of the learned distance metric between the learned distance metric and the true clustering of the data set. Okay, so one example of the clustering error is defined like this. Okay, something wrong. So the error, so we compare H. H is the hypothesis partition function, and P is the true partitioning function. So basically, this error function is a weighted sum of two types of pairwise errors. So in clustering a set of data points, after that we make some pairwise prediction. So whether two data points, they should be together or they should be in different group. And the two types of pairwise errors are, so first of all, if two data points should be together, but we separate them apart, this is one type of error. And if they should be in different groups, but we put them together, this is another type of error. So the whole error function is just a weighted sum of the two types of pairwise errors over all the pairs of data points in a labeled data set, and weighted by the distance d between each pair of data points.
So, but that distance that you're using to measure the error, is that the distance that you're learning?
Right.
Given by A, or what?
Okay. Distance metric is d. But H is a combination of d and the clustering algorithm A. So H is a partition function, yeah.
So what was the motivation for doing this weighted error instead of just kind of counting the number of errors?
Motivation is that we want to incorporate the distance into this error. So we can, in the learning stage, we can minimize this error by updating the distance metric. Right.
The data.
Right.
So if you use it in that and in the error metric,
Yes, yeah, I understand, yeah. Actually, I think it's okay, actually. So in Michael Collins' work, so he proposed a way to train the raceful feature vector by minimizing some global error, and also they incorporate the features, the weights in the global goal, and he claims that he proved actually it's okay. It converged to the true, the local optimal.
so there aren't like,
Weights.
there isn't like a trivial solution where the distance metric is say 0 for everything. You don't run into that.
Yes, yeah, I understand your question. So if the d here is 0, then you will get a global error. But in reality, you can avoid that problem. You try to find something else instead of that one.
You're thinking of the maximum distance. Doesn't that make you wildly different about what the distance is? I mean, just because choosing the maximum distance of two points, right, that's what you're doing there. That's
Right.
what you're doing. It seems that two problems that are very similar, you're weighing your positive versus negative very differently without
Okay, so right, so I agree with you. Sometimes you can get some exception, but this is one example of the error function. And actually, we did some more work in this area. So if we choose another error function, a different one, actually this new approach, SDC, is equivalent to variant of the EM algorithm. So if we expand the EM algorithm with label data and change it in some way, the SDC will be very similar to that algorithm, expansion of the EM algorithm, not the standard EM algorithm. So for this, for this arrow function, I don't have further explanation for that. We just choose this because we want to put the distance metric into the arrow function, and so we can update the distance metric to minimize the arrow function. But we can choose other arrow functions. Okay. So in our experiments, for SDC, for the supervised discriminative clustering approach, we apply it in the entity identification problem. So given a set of groups, we cluster them into different, a set of names, we cluster them into different groups. The data set, the original data set is the track data set. It's the news articles, New York Times news articles. So we use 300 news articles, and we tracked about 8,000 names in the 300 documents, and we do the annotation ourselves. Yeah. So in SDC, in training stage, we use the single link clustering algorithm. Basically, we train a linearly weighted distance metric for the single link clustering algorithm. And in testing, we apply the learned distance metric with the same clustering algorithm for the new data. And here are the results for testing. So you can see the SDC can outperform many existing approaches significantly. So here is the here we try to learn some similarity metric from the pairwise classification task, and then we apply the learned distance metric with the clustering algorithm in testing. So here the learning and the testing stage are disjoint. Okay. So here we just do pairwise classification. So these three, we just do pairwise classification. Here we do clustering over pairwise classification. And our SDC, we train a distance metric with respect to a clustering algorithm, and we use the same algorithm and the same distance metric in testing. So it can outperform its other approaches significantly on all three entity types. Okay. Okay, that's the clustering work. So now we'll go back to the entity identification problem and talk about the third challenge, another challenge. How to implement a global model to predict what entities are mentioned by a document. Okay. And this generative model is based on more observations. So first, names in the same document and the names in different documents, they have very different, they can provide very different information in entity identification. So if two names are very similar to each other in a document, probably they will refer to the same entity. But if two names are similar but they are in different documents, probably it's very likely they refer to different entities. Okay. Another observation is related entities tend to occur together in many documents. Like George W. Bush and the White House, they occur together in many documents. Another thing is in one document, there is usually a long name for entity, like John F. Kennedy. And all other names are just variations of this long name. So typically, the long name could be the full name of this person. And all other names can be viewed as being transformed from this name by string transformation. And we identify this long name as the representative of this entity in this document. And also, most important, one difficulty in this kind of task is it's very hard to annotate data. So given many names in different documents, it's very hard to annotate which name refers to which entity because we need to go over all the names in different documents. So probably in this kind of task, we hope that we can have an approach that can use limited labeled data or unlabeled data to do entity identification. So for this purpose, we developed a generative model that can be trained with unlabeled data and can exploit the information based on the observations. Okay. So before I talk about the generative model, it's a generative probabilistic model. So this, I need to first talk about the generation process of a document underlying the model. So the generative model is based on this generation process. So here I care about how to write a document and how to generate names in a document. So suppose I'm an author, I want to write this article. Here I care about names in this article. So I will study how to generate names into this article according to a probability process, probabilistic process. Okay, at the beginning, I have a set of entities in my mind. So I know a lot of people, locations, and organizations. But in this article, I want to talk about John F. Kennedy and Martin Luther King. So at the first step, I choose a subset of related entities and put them into this article. And this is done according to some underlying probability distribution. So we can define the probability of choosing a subset of entities, and we just sample according to this probability to get the entities in this document. And in the second step, for each entity, I choose the representative for this entity. I choose the longest name for this entity in this document. So for John F. Kennedy, I choose President John F. Kennedy as the representative of this person in this context. So in another document, in another context, probably I will say Congressman John F. Kennedy instead of President John F. Kennedy. And this is done also according to some underlying probability distribution. And after this step, I will get the set of representatives of the entities in a document D. Okay. So previously, I get a set of entities in a document D, which is ED. And here I generate the set of representatives in document D, which is RD. And in the last step, for each representative, I transform it into a set of short names. So these names are the actual mentions of this entity in a document. So for President John F. Kennedy, I choose Kennedy, JFK, and President Kennedy as the actual names I will use in this document. And this is also done according to some underlying probability distribution. So what's the probability of choosing a mention given a representative? And after this step, I will get the set of actual mentions in a document D, which is MD. It's a set. So the lowercase m is the one single mention. Okay. And the generation process can be summarized in this graph. So we have 3 generation steps. And in each step, we have different underlying probability distributions. Okay. And the entity identification, based on this model, the entity identification problem actually is a reverse process of this generation process. So typically, when we have a set of documents, we observe the actual names in a document. And we need to figure out what are the most likely entities and what are the most likely representatives for these names. Okay. And this is formalized as an inference problem based on the model. Suppose we know the model, we know the probability distributions, then we can compute the joint probability of ED, RD, and MD given this model. And we just find the most likely entities for these mentions. Okay. So now the problem is how to learn the model. So we suppose we have the model here. Okay, and we don't want to learn the model with label data, so we use the EM algorithm to learn it. And so in the learning stage, we only know the mentions in each document. Suppose we have a collection of documents, and we try to learn a set of model parameters that can maximize the joint probability over this document. And we also want to find out the ED and RD for each document in the same process. Okay. And the model parameters we want to learn include the prior probability over each entity and the conditional probability between two entities. So the entity co-occurring dependency is incorporated into the conditional probability between two entities. So what's the probability of choosing E2 given E1 has already been chosen? Okay. And also the appearance probability. So what's the probability of a mention being generated given the representative?
I'm sorry, I'm a little confused. So earlier you said that the probability of
Okay. So you mean here?
Yeah. Oh,
Right.
I'm sorry, I thought you said.
Okay. Okay. So yeah, in our experiments, we compare the generative model with the pairwise classifier. Okay. The pairwise classifier is based on the features I mentioned before, and is trained with label data. In the generative model, it is trained with unlabeled data. Okay. So it's very surprising that the unsupervised generative model outperformed the supervised pairwise classifier. And it's a very interesting problem. So we studied this problem further, and we found that there are several advantages related to the generative model. Okay. So one advantage is the generative model is trained and makes inference globally. So when you train the generative model, you consider a set of documents. You consider many names together. And it also separates the within document problem from the across document problem. Okay. And another advantage is the generative model is unsupervised, so it can be trained with more data. So this is not a very fair comparison because the generative model is trained with more unlabeled data. Okay. So as a quick summary, so I talk about the concept-based text understanding and mining, and also the core task entity identification and tracking. And I also talk about the several approaches we have to this problem. And in addition to the work in this direction, I also did some work in in natural language processing. So we developed. So this is not relevant to this talk now, but we developed the first and still the state-of-art learning-based question classifier to map English question into some semantic category for question answering system. And I also did some work on shallow parsing and lexical semantics and question answering. Okay. So in the future, I will continue to work in this direction. So for entity identification and tracking, probably I will also apply it to the web data instead of just news articles. And I also want to continue to study the machine learning approaches to this problem, like semi-supervised learning, like clustering approaches, like kernel-based learning. And another big direction is applications. So if we can do the concept identification and indexing, we can apply it to many text-related tasks, like information retrieval, information extraction, question answering. And I want to apply it to these tasks and see how it can help these tasks to get better performance. Okay. And another direction is to link text information with databases. Okay. So okay. And we call it semantic integration across text and databases. So by link text and databases, we can have very efficient access to text information. And we hope we can link them based on the real-world concepts in the same way as before. Okay. So one specific example of the future work is to apply the previous work into search. So instead of search by strings, we hope to search by concepts. Okay, so here, one example is here. So this is the current MSN search result. So if I want to find information about the former president, George Bush, I input the keywords in MSN search, and it will return the documents that contain the name George and Bush. Okay. But only in this one, this article is related to George Bush. Actually, other documents, other web pages are related to a different person. Okay. So by string matching, the information retrieval engine cannot disambiguate different persons. Okay. But if we can implement the concept identification, we can organize the information according to different persons and try to return information in a better way and try to get rid of the noise. Okay. So if we can do that, so when we want to find information about George Bush, we still input George and Bush. The system can return the information about the most prominent Bush instead of information about all Bushes. And probably it can also provide a list of possible Bushes. So you can choose which Bush you are looking for and get the correct information. Okay. So I'll use this example to show why do we need to link text with databases. Okay. And why the semantic integration over text and databases is a big problem, and it can have many, many applications. So this is an example of the international movie database. So in this database, we have information about famous actors. This is in a database. And we also have everyday, daily news articles about movies. Okay. So these are text documents. This is a database record. And so we hope to link them together. So why do we want to do that? So suppose I'm a user of this system. When I browse the information about Woody Allen, I read many pieces of information about him. So what I want to do after reading the information is probably I want to read some recent news articles about the same person, about this actor. So I need to go from the database side to the news articles. And sometimes when a user reads the recent news, he also wants to find out more information about the actor. So he wants to move from the databases move from the text side to the database side. Okay. And so that explains why do we need to link database and the text together, because we want to find information on both sides in an easy way. And there are many advantages of doing this. So basically, with a large collection of text information, we hope that we can construct some databases or knowledge bases from these text information. And we also hope to implement an efficient and intelligent access to textual information by linking it to databases. And by linking information together, we can find some hidden knowledges that we don't know before. Okay, so I need to thank a lot of people that helped me with this work. And there is also some entity identification, person identification here. Okay. And the conclusions I want to convey in this talk are first of all, text understanding and mining tasks need to move from mention level processing to real-world concepts. And the second of all, clustering can involve learning and can handle supervision. And last, the semantic integration of text and databases can have significant applications. Thank you.
Can you comment on your question answering of this? If we had a perfect, you completely solve this problem, how would you use that for question answering?
For question answering. So let's see. have some extra slides. Actually, it can be applied to question answering in many different ways. So first, we can do name expansion. So if we know which names are related to which entity, so when we ask a question about a person, we can do name expansion. So given a name, we can find other likely name of the same person and use it in search, in question answering. Another application is, so if we want to ask a question about what is Bush's foreign policy, and we don't know which Bush the question asked for, we can compute the prominence information based on some statistics over this system. And we try to return information about the most prominent Bush. And also relation recognition.
For the first one there, for the name expansion, do you know if for track record in terms of tasks, how often we're failing because of names? Is that a major problem?
So I don't know. I don't remember the exact number, but I think we did some statistics before, maybe 10% or something.
10% of the failures are.
Right.
So I assume that most people will ask about your double in that case, but if you're doing this on the query side, without looking at the context of the document returned for the foreign policy, right? If I ask what are Bush's latest outreach and I refer to cases,
Right.
I'm going to get split because you replace Bush there with George Bush, and I'm not going to find output from your double.
Okay. Right. Yeah, I agree. But this is.
But in this case, foreign policy helps me when I ask that question. I don't know what Bush is, but the search is going to do that with ambiguation for me because of the context.
Yes, I agree with you, but I have two comments. So first, then it needs you to define the query in a better way. So it's a trade-off between query and your system. So you are asking for users to give you better queries instead of you improve your system. And another thing is this is a real question in the trial computation, and it asks for information about George Bush instead of George W. Bush. So sometimes it's hard to tell from all in the names. So you have to have some statistics over the entities and try to find what is the most likely entity you are asking for.
So wouldn't the document collection be ambiguous there for the exact thing? Then I don't just predefine each entity you're looking for double like, shouldn't I just look at this was a track collection from 10 years ago?
Right.
5 years ago.
Right.
Then it's probably going to be George Bush, not
Right.
George W.
Right.
I know, I prefer not to do this unless I make that on the collection I had.
Okay. Yes. Okay. So actually, the internet is changing, right? The information is changing. 10 years ago, the most prominent Bush is George Bush. But also, you can implement the system using new articles. Then you will get George W. Bush here for the most prominent Bush currently. Okay. So now we run the model over 8,000 names. It takes about 20 minutes for training. But we didn't do any optimization. So actually, we can do many kinds of optimization. So first of all, we can do run the model on different. We can separate data like web pages into different groups, and we run the model over different groups, and we can hierarchically run the model and get results. And another way is this is only for training. So you can do you can implement an incremental algorithm. When you train the model, you can use it to cluster new documents in an incremental way. Right. Right. That's true. After a while, we need to do hierarchical clustering again to retrain the model. So, actually, we didn't do that because it's very hard to annotate data. Yeah, but we thought about this. Yeah, we thought a lot about this. Yeah, I think it can be improved.
Can you say a few words about text summarization of the input?
Yes, I think it is also pretty much related. So in text summarization, you need to find pieces of information from different sources or different parts of a document and try to construct the summarization. But here, if you can identify the entities behind names, then you can integrate pieces of information together based on these concepts. Then, based on this work, you can do a better summarization because you know these documents are related to this person. And these pieces of information are related to this person, so you can summarize in a better way, I think.
So you're talking about selection of symbols.
Right. Selection of, yeah, one way is selection of sentences, another way to select different documents, right? Like in news, you have different pieces of news about the same event, and you want to integrate them together and provide a short summary of the news about this event. Then you can do that.
But how about the sequential structure?
Okay. I think it could also help in some sense because you know different variations of these person names. After you know they're all related to this person, you can identify the information about this person from different sentences.
So for text summarization, actually, you're limited by how good your name entity recognizer is, right?
Right.
So you're never going to map. The purity distance is not going to handle First Lady to Laura Moon.
Right.
And if the name entity doesn't mark it as an entity.
That's true.
Right? So that's one problem. But the second question I had is, well, that was more of a do you have a distribution, I know, an entity ambiguity distribution in your collection? So I know, I would assume that most entities, when you just pick randomly 8,000 entities, right? Some articles have 8,000 instances of entities. Most of them will be one, and then you may have like two. Washington might have like
I can show my our baseline result to use some simple ways to do that. This can give you the impression how difficult the problem is and how ambiguity. What is the ambiguity? So the baseline result is about 70%. So if we only predict as positive if two names have identical writings, and by using the fixed similarity metric, it can get to about 90%. But actually, our approach can improve maybe 5% after that. So we use very simple, and this is not very simple. This is the state of art fixed similarity metric to match names. It can get to about this performance, but we can improve after that.
Not quite what I'm thinking, because now if an entity has an entity that has a lot of rewriting into has a very large influence on that score, right? So you have a lot of pairs from there.
Right.
And
Let's see. Can you say it again?
So basically, for how many entities?
I see. I understand.
Ambiguity at all?
I think I would say there are many, because the data set we choose, it contains information about Bill Clinton, Hillary Clinton, and Bush, and George W. Bush, many kinds of these kind of things. Yeah. Okay, I think the first approach we proposed is the result of feature engineering. So actually, it's shown by this graph. So for our classifier, pairwise classify, we use the features I mentioned before. But other people, they use different features. So you can see the improvement. This is our result. So I think, yeah. So because, no, TF-IDF is a fixed similarity metric. So it has just compare the two strings and get some similarity. So it will get this kind of result. But Marlin is developed by Bianco and Mooney in UT Austin. They implement the classifier based on SVM and based on a different feature set. And we use the relational features and structural features. You can see it can improve it. Okay, thank you.
Thank you.